Hello everyone, welcome to my talk. This is about porting OCaml to run on bare metal devices, particularly the nRF52 platform. For this, we're going to be using RIOT OS and OMicroB. The particular board that we're targeting is the nRF5240. It uses a an ARM Cortex M4 processor. It has 1 megabyte of flash memory. This is where we might store code, things that aren't modified very often. And it has 256 kilobytes of RAM. And this is where we will dynamically allocate memory. In particular, because it's an ARM chip, it uses an ARM instruction set. This is very different from the x86 instruction set that desktops and laptops normally use. And so we have to take this into account for development. Going back to what we actually want to do, we want to take our nice, lovely abstract OCaml code and we want to translate it into something that this board understands. Here we want to print something to the terminal. How might we do this? There are two ways we can do this. The first is to use native compilation. Native compilation takes OCaml and it compiles it down to native code specifically for the target device. And then this is run just like any other standalone program. Luckily enough, there is an ARM backend to the ocamlopt compiler. However, this is only half of the story. As well as the compiler, there is a linker that we need. We need to link the object code together into an image that targets the platform. And remember that we have separate flash and RAM. How do we tell the linker where to put code, where to put the stack and the heap? This is a lot more in depth than just saying it's ARM. So this is quite difficult, and especially at the beginning of the project when I wasn't very familiar with the board, with the internals of OCaml, this didn't seem like a particularly easy option. So the second option is to use bytecode. We can compile OCaml to a portable bytecode, and this is like assembly, but imagine it for a virtual machine. This is interpreted by an OCaml bytecode interpreter. With bytecode, it's the interpreter itself that is compiled and linked to run on the device. We then compile OCaml to this bytecode, load it onto the device as a simple array of data, and the interpreter just runs on it. Now, it might seem that we've just delayed our problem for later. I said before that the issue with native compilation is that we need to do our complicated linking. But luckily enough, the OCaml interpreter and the entire runtime in general is written in C. And C is slightly more popular for embedded development than OCaml. And so ARM provides an entire toolchain for C development. A toolchain contains tools like a compiler, linker, debugger, things that are very useful for development. And so the runtime implements the interpreter, of course, as well as exceptions, garbage collections, stacks, the runtime. This is a section of the interpreter. You can see that we handle different bytecode instructions. This is C. It looks slightly strange, but it's just because the OCaml runtime is filled with preprocessor macros. So this is just, next here is just a go-to, essentially. One small detail that I want to pay attention to is, oh, that did not work, is C calls. The bytecode is a very high-level abstract language. It doesn't have many architecture-dependent specific instructions or ways to interact with the lower-level system. The ways that it does have are these C call instructions. It can interact with the runtime. It can interact with C functions that you've defined yourself. And you have an array of these C functions available, and you can call them from the bytecode itself. And these C functions are called C primitives. And these will be very important for later. So a current overview of what we have at the moment. We have our OCaml code that is compiled to a bytecode. This is given to the OCaml runtime that is compiled for the device. And at runtime, the OCaml runtime and the board talk to each other, and the runtime, the interpreter executes the bytecode. There's a few issues with this. This is a very simplistic view. Fundamentally, the OCaml runtime and the board speak very different languages. Again, it didn't work. There we are. The OCaml runtime wants abstract things like I/O and that sort of stuff. The board only speaks in pins and pointers and bits and bytes. They speak completely different languages. Not only this, a second more difficult issue is that the board doesn't just start ready to run. There's an awful lot of initialization that needs to be done to get it into a state where it can run the runtime. For example, initializing the processor, registers, exception handlers, stacks, that sort of thing. There's a third, even worse issue. Here before, I assumed that we had the OCaml runtime in a state where it could run on the board, but that would require that we have the right compiler and linker flags to give to the ARM toolchain to compile it correctly. Just having the ARM toolchain isn't enough. It's not enough to tell them, oh, it's just an ARM device. We need to tell them the layout of the board, what features are supported, and this is very in-depth. The solution to this is RIOT-OS. RIOT-OS is three useful things. It's an energy-efficient microkernel for interfacing with the board. This means it can sit between the OCaml runtime and the board and handle, basically be a translator. Secondly, it does the background work of initializing the board and the CPU with exception handling and threading and everything that we need to do beforehand. And third of all, it provides a robust build system for generating flags for compiling and linking that creates an image that can be flashed to the device. And this build system is really very useful. And so an overview of the current runtime. We have our bytecode given to the OCaml runtime. When the runtime wants a service from the board, it asks RIOT, and RIOT has an implementation specific, has a board specific implementation, and same in the reverse direction. Yes. Now going into more depth in the build system, we have a few steps. We specify the board that we're targeting, and RIOT then works out all of the required compiler and linker flags needed, as well as pulling in all of the C files, linker scripts that it has specific for that board. There's a C file for the Cortex-M processor, for the board, for the peripherals, and it compiles those, pulls them in and links them, and you never have to worry about it. Now, how do we actually compile our application? We have an application directory. All the C files in that application directory will be automatically pulled in by RIOT, compiled with the correct flags, and included in the linking step. So our strategy for this is going to be taking our OCaml files, we're going to compile them to bytecode, and then we're going to dump that bytecode into a C file that just has the arrays of data as simple C arrays. And luckily, OCaml C provides easy functionality to do this. Third of all, the OCaml runtime itself, we compile with the same ARM compiler, the same flags. We pack it into a static library, and then we inject it into RIOT's linking step so that the runtime is included in the final image. And this uses the correct linker flags, of course. So an example of what we going through the pipeline, we have our nice, simple OCaml program, and we want to compile it to bytecode and then dump it to C. And it's a very simple command line execution thing to do this. What this produces is a C file. And this is some of the structure of that. You can see that we have our array of code, data, sections, and then we have a call into the entry point of the OCaml runtime where we pass in that data. This does the required runtime initialization and then starts the interpreter running on the code. There are some other parts of the C file. We also include the external C functions that our bytecode might call into. Remember how I said before, the C call sort of API. It might seem weird that we're including an arccos function in a program that very obviously does not use arccos. And this is because we are kind of reusing functionality from building an OCaml interpreter that we're not really supposed to be using for in a way. Generally, when you're making an interpreter, you're making it for any program. Any program should be able to run on that interpreter, and so we include the functionality of all possible functions that could be called in the runtime. This case where we're building an interpreter for a specific program, we don't really have a way to do this, and so we have a lot of wasted space, including implementations of functions that aren't used, and so this will come up later. A sort of summary of the build system: we have our OCaml file, we use the system ocamlc to compile it to bytecode, dump it to C. We compile the runtime using the same RIOT flags. We pack it into a static library. We add it to the link flags environment variable. And we have our C file in our application directory. And then RIOT just builds it. And it pulls in all of the RIOT specific files specific to the board we're targeting, compiles everything, links it together, and produces a hex image that can then be flashed to the board and will just run. So a little test program, classic hello world, just to see if it works, and it does. When run on the board and connected to a terminal on your computer, it prints out hello world. This is very, very nice. So just to sort of drill down the specifics of what's actually happening in this call, we have our bytecode, which is just hex values. This is an opcode, perhaps a pointer to the string we're trying to print. This is seen by the OCaml interpreter. It's parsed as a C call instruction. We look up which particular function is being called in the primitive table. We jump into that C function, the caml output, that is given OCaml values. We convert those OCaml values to C values, and we call some write function. The OCaml runtime doesn't know how this write function is implemented, but RIOT provides it. And it is the implementation specific to this board. And so there's a very nice separation of responsibility between levels. And you can very easily swap out, for example, the board for something else, and it will just work. There are some issues with using the standard OCaml runtime. First of all, it produces a very large image. A sizable program can very easily exceed the flash memory. The program from before, our little hello world program, links to an image of 435 kilobytes in size. Sorry, that's supposed to be bytes, not kilobits. If we instead want to have a slightly nicer programming experience and use the printf module, this produces an image of 743 kilobytes in size. Just including the printf module, not exactly a powerhouse, it increases the size almost double. And remember, there's only 1 megabyte of flash. This doesn't bode well for writing sort of non-trivial programs. But let's try and run this and see what happens. Not enough memory. Now the issue with this is module instantiation. we're trying to pull in the printf module and call a function from it. And the way that the OCaml runtime does this is it has to instantiate a module, and this uses this dynamically allocates a lot of memory, specifically in RAM. Remember, we have a very small amount of RAM. Now, this can be on the order of, hundreds of kilobytes of memory dynamically allocated. On a desktop, this is nothing. This is easy. On our little board, poor little board with only 256 kilobytes of RAM, it immediately crashes. And so this is pretty bad. We can't use modules. And I don't know if you've ever programmed in OCaml, modules are quite useful. So we need to change our strategy. And the way we do this is by using a different project. People have already solved this problem. OMicroB. This is a project that allows you to run OCaml bytecode on extremely memory-constrained devices. Think 2.5 kilobytes of RAM. This is quite literally 100 times less than what we're targeting. So obviously they're doing something right. It does this through a number of ways. First of all, it uses a very highly customized runtime. And as well as this, it does multiple static passes over the bytecode itself before even running it to reduce its size. It targets the PIC32 and AVR microcontrollers, but we can modify it to target our nRF52 microcontroller. So there are two nice optimizations that OMicroB does. First of all, the bytecode is cleaned of redundant information. OMicroB uses another project called OCaml clean, and this goes through the bytecode and removes all the redundant information, of which there is actually quite a lot in the bytecode, but generally it's not that big of a deal. This also includes C primitives, as we talked about before. Usually all the C primitives are included, but this allows us to strip out the ones that aren't used, which is a huge amount of space saved. The second optimization is that the interpreter itself is stripped of unused bytecode instructions. What exactly does this mean? Remember, we're targeting a specific bytecode program. If that program never actually uses a particular instruction, there is no reason for the interpreter to ever need to handle that instruction, and so we simply strip it out. And this, again, saves quite a bit of memory. The main optimization, however, and is what fixes our module instantiation issue, is this simulation. OMicroB does a simulation of the bytecode interpreter. It has a virtual stack, heap, accumulator, program counter, and it runs the bytecode on your computer. And so this will do the module instantiation for you on your powerful computer so that it doesn't have to be done on your poor little microcontroller. It does this up until the first I/O, at which point the program obviously has to be run on the device. At this point, it has a sort of snapshot of the state of the system, and that state is dumped into a C file, very similarly to how OCaml C did before. And so you can see we have a stack, a flash heap, and this contains sort of the intermediate state of the system at the particular point that it stopped. So this is an excerpt from our 10+5 program from before, and 10+5 doesn't have any I/O. And so you can see our bytecode simply contains the halt instruction because it's been simulated up until termination. And so the result of 10+5 is probably stored in the flash heap somewhere. As well as this, you can see in the array of primitives, since we've simulated up until termination, we're not going to be using any more primitives. And so the array is empty. And this reduces the size of the final image greatly, of course. Obviously, this is quite an extreme example, but you can see the situations in which this would be extremely useful and would reduce the size of the runtime significantly. An overview of how we've changed our build system with OMicroB. It's the beginning phase that is now slightly different. We have our ML file. Using the same system OCaml as before, we create our bytecode. We use OCaml clean to clean that bytecode to reduce it, significantly reduce redundant information. Then OMicroB does a simulation of that bytecode up until the first I/O, at which point the state is dumped into the C file. The OMicroB runtime is then simply included into the C file with a standard preprocessor include. This C file is stored in the application directory, and RIOT just pulls that in along with all of its specific files, compiles it all together, links it, and produces the hex image. There are some limitations with OMicroB, particularly it's actually too optimized. It doesn't have a lot of the runtime functionality that we might want. For example, we don't have pipe-based I/O for terminal output, which is very nice and useful. However, this isn't actually an issue. You're able to add external C functions with the kind of OCaml external keyword. So these can be implemented yourself. You can see we define an external length function, and then we implement it in C. And then this can be simply used in OCaml. Now you might notice I'm not actually showing you any hello worlds from OMicroB. That is because it doesn't currently work. OMicroB targets OCaml 4.7. I'm trying to target OCaml 4.12, and there is quite a big difference in the structure of the bytecodes, in particular the closure environments. Fixing this would be pretty simple. It's just updating OMicroB as well as its dependencies to 4.12, but that requires an in-depth knowledge of the structure of the language, which I don't have at the moment. And two, I ran into this issue last Thursday, at which point I thought I should probably start documenting what I've done and starting on this presentation. So this is a problem for the next person to fix. Plans for the future. The reason we want to get OCaml running on these embedded devices is so that it can interact with the outside world. OCaml has a very nice way this can be implemented, as I said before, defining externally defined functions in an OCaml module, so that in OCaml you can call this function, which is then implemented in C. So for example, this read sensor function is essentially a wrapper for a RIOT implemented function. And so this sort of connects RIOT to your very high level OCaml programming. And this can be implemented, as I said, quite easily. As well as this, the amazing thing about RIOT is how modular it is and how sort of separated everything is. If I wanted to target a different board, I simply change the board variable, and the RIOT build system takes care of it all. If I want to use different modules, if I want to use GPIO pins, timers, you just add the module in the make file, and it just does it for you. And so this is a huge amount of generalizability to get OCaml running on a huge range of devices. RIOT supports a ton of boards and continues to support more as time goes on. And that is everything. I just want to say some quick thanks. Magnus for supervising, Lucas and Romain for knowing quite a lot about OCaml, as well as embedded developments. Obviously the RIOT team for making RIOT saved my skin. The OMicroB team for making OMicroB, and everyone at Tarides as well for being great. That is it.